All right, Unit 9, Applications of Thermodynamics. We're at question 61, so let's get to that question. All right, let's see. It gives us this reaction. It's methanol becoming carbon monoxide and hydrogen gas. We have a delta H there. The reaction vessel goes essentially to completion. The reaction takes place in a rigid insulated container. Okay, so it says it goes to completion, essentially to completion. This is a reference to delta G being negative, right? This is saying it's thermodynamically favorable. We know that the delta H is positive as well. So what is the delta S? Well, okay, I get what they're saying here. That's true. But we also know that the delta S must be positive. You know why? You have one grandkid here becoming 3 grandkids. So delta S must be positive. So this statement is true. Now, I do want to focus on this, what they're saying here, but we'll wait for another question to bring that out. All right, when a magnesium wire is dipped into a solution of lead 2 nitrate, a black deposit forms on the wire. Which of the following can be concluded from this observation? What I would say, the first thing is that delta G is negative. Why do I know delta G is negative? Because you didn't add any energy, you didn't add an outside power source, and all of a sudden it's just starting to happen. Okay, so what's happening? What is the black stuff that's forming on the wire? Well, in the solution there's lead 2+. It must be gaining a couple of electrons and becoming the lead that you see on the wire. Okay, so this the lead is gaining electrons, therefore the lead is rigging. Okay, if the lead is rigging here, if it's gaining electrons to become Pb, yeah, then it means, let's see. Oh, I get it. So if your delta G is negative, we've established this, that your E cell must be positive. So your E cat minus your E anode, if your E cell must be positive, right? If your E cell must be positive, then your E cat, this guy, has to be greater than this guy. If he's not, then you're going to end up with a negative number. So your E cat, who's our cat? Our cathode happens at the place where it is being reduced, red cat. So Pb2+ is our cat, right? So the standard reduction potential E for Pb is greater than that of Mg. That's true. The cat better be greater than the anode, or if the anode was bigger, then the E cell would be negative. All right, number 63. Ammonium chloride is added to water. It dissolves and the temperature of the solution decreases. Temperature of the solution decreases, that means it is endothermic. Okay, so delta H is positive. Temperature of the solution. Also remember, the formations of bonds is exothermic. The dissociation of bonds is endothermic. So NH4Cl disassociating water would be endothermic. It would also, you would go from NH4Cl, you would also go from NH4Cl to NH4+ and Cl-. You would increase in your entropy. So your entropy would have to be either this or this. The correct answer that satisfies both criteria is A. Okay, 63. All right, let's look at this 64. Which of the following equations represents a reaction for which the standard entropy change is positive? We are becoming more disorderly, okay? All right, A, we have 3 grandkids becoming 2 grandkids. That's good. One of them left the house. Now it's not as crazy. We have on this side 3 grandkids. Ooh, 3 grandkids becoming 2. What's in between grandkids and grandparents? Well, I guess just parents. Okay, so this is becoming more orderly, less crazy. This is a grandparent and becoming a grandparent with a grandkid. That's definitely increasing in disorder. Okay, so that's my main candidate right now. And then you have a grandkid a grandkid with two grandparents becoming two grandparents. That is less disorder. So the correct answer is C. We have an increase because you're getting more disorder when you get those gases. Those gases have way more entropy or way more disorder. Number 65, which of the following processes involves the greatest increase? So this is greatest increasing. So we have 2 moles of gas becoming 2 moles of gas. That is the same. We have 4 moles of gas becoming 2 moles of gas. That is decreased in entropy. We have 2 aqueous things becoming 1 solid thing. That's decreased in entropy, less disorder. We have 3 moles of gas becoming 1 mole of gas. That's decreasing as well. But look at the last one. You got 1 grandparent. You got 1 solid becoming another solid plus a grandchild. Yes, that is going to increase in disorder. The correct answer is E. All right, 66. 66. Which of the following reactions is not thermodynamically favorable at low temperatures, but becomes favored as temperature increases? Okay, let's talk about this. All right, delta G is equal to delta H minus T delta S. Okay, it's not thermodynamically favorable at low temperatures. See, at low temperatures, okay, let me give you, let me make copies of this. All right, at low temperatures, this guy right here, he becomes invalid. Okay, you know, I don't like that red on red. Let's do something beautiful. Okay. He becomes invalid at low temperatures, right? So if it's not thermodynamically favored at low temperatures, that means it is the entropy is not involved, right? But that means it is enthalpy driven, okay? So if it's not thermodynamically favored at low temperatures, the delta H must be positive, okay? This is positive. Now, but as you increase temperature, now I think I made it look too crazy, so let's move that out of the way. Let's go back to this. Ooh, no, I'm sorry, T, I took your head off. Okay, but now let's see this. But as temperature increased, guess what? This guy became invalid. He didn't matter anymore because temperature made the entropy matter more. So entropy must be super positive, but as the temperature increased, it got more positive, so positive that when you got a positive minus a bigger positive, a positive minus a bigger positive is a negative. That's what happened here. So what we just figured out is that delta H and delta S were both positive to begin with. So what's the possible answer? Bingo. Everything else has other delta S's and delta H's. You use the delta H and delta S that are both positive, and that's the only one that has it. The correct answer is B. All right, number 67. When water is added to a mixture of NaO2 and S, a redox reaction occurs as represented by the equation below. Ooh, we have a negative and negative. Okay. All right, that means this. When you have your, okay, and let's bring him with us. You know, he's good. He's a good guy. All right, so let's take a look. We got a negative delta H. We have a negative delta S. Yes, they're both negative. Delta S and delta H. Now, see, this is going to become negative and a negative minus a negative, okay, that's a positive. Now, I just want you to see that your enthalpy is making this you thermodynamically favorable until your temperature gets too big. If your temperature gets big enough, it'll make your delta S really, 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 really powerful. And the T delta S will overcome the delta H, okay? So, which of the following statements is true about the thermodynamic favorability of the reaction? It is thermodynamically unfavorable. No, it's thermodynamically favorable as long as temperature is low. It's thermodynamically favorable as driven by S only. No, that's not true. It is thermodynamically favorable Do I got to do the numbers? And is driven by delta H. I guess you can do the numbers. You should know that temperature 298 is a very low temperature, and I mean, I know that feels very subjective, but in chemistry, 298, especially when the Kelvin can go up to 1,000,000, but but it can't go any below 0. I mean, 298 is really low. I guess you should plug the numbers in to try them out. If you do plug the numbers in, you need to remember to convert your your delta S into kilojoules. I'm not going to do it, and I know. I just don't. It's just not worth it. All right. Whoa! Look at that. HCl can be synthesized from H2 and Cl2 as represented above. A student studying the kinetics of the reaction proposes the following mechanism. So slow, fast, and he has Kp going on. Whoa. Which of the following statements identifies the greatest single reason why the Kp for the overall reaction has such a large magnitude? Yeah, why is K so incredibly big? Look at that K value. Woo! Okay, it means a lot of products, no reactants. Well, I'm going to tell you this. You know what your delta S is? 0. Because it's two gases becoming two gases. So really, if your delta S is, look, think about this. Delta G is equal to delta H minus T delta S. If this is 0, then really the answer is delta G is equal to delta H. So what's making this thermodynamically favorable? What's making delta G so negative? Well, delta H must be super negative. Yeah? So the correct answer is D. The value of delta H for the overall reaction is huge. And it must be negative, which is making delta G be huge and negative, which makes K super positive, produces a lot of products because the reaction is therefore spontaneous. Okay, 68. 69. All right, an electrolytic cell based on, electrolytic cell? Zinc and copper. What? Half cells, observed footage was found to be, okay, got it. All right. So your E cell turned out to be positive here. Wait, how is that true? It just said that you're an electrolytic cell, but what? Okay, whatever. All right, all right. The observed footage was found to be 1.0 volts. It was less than, okay? So, all right. Whoa, this is cool. All right. Delta G is equal to negative NFE, yeah? But also delta G is equal to negative RT-ln K. And I've done this a couple times, but remember, this thing and this thing, they're just both negative numbers, right? A negative times a positive, negative times a positive. So in other words, your E has to equal to ln K. Well, what did we notice about our voltage? Our voltage was 1.0, not 1.10, so our voltage decreased. How would we get our voltage to decrease? That means our ln K has to decrease. How does ln K have to decrease? Well, ln K is products over reactants. If you want that number to get smaller, you have to increase the amount of reactants, yes? You have to increase the amount of your denominator to get that number to go lower. So we want more reactants. All right, what could be correctly said about this? Let's bring this down with us so we know. I didn't bring the top of the E with us, but okay. Okay, so we want more reactants. What's going to give us more reactants? Well, first of all, remember what we're dealing with here. Okay, I would make a Le Chatelier's seesaw here, and you would see that there was Cu2 plus over here. There's Zn2 plus over there, right? You know what would make a lot more reactants? That would. If you made zinc 2 plus heavier, then to get back to equilibrium, it would form more Cu2 plus. And you would get more reactants, and that's exactly what we're looking for. So give me something that says that. The copper electrode was larger than the zinc electrode. What? No, those are one of those is not even part of, neither of those are part of equilibrium because they're both solids. The Zn2 plus electrolyte was Zn that, well, what? I don't understand. The Zn solution was more concentrated than the Cu2 solution. More concentrated. That is correct. If you have more Zn2 solution, that side gets heavier, so it creates more Cu2+. If it creates more Cu2+, you have more reactant than product, right? If you have more reactant than product, then your LNK goes down, and that means your E cell goes down. The correct answer is C. That's a good question. Very, 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 very good question. All right, number 70. Fe2 plus and Zn yields Fe Zn2 plus. The E cell is 0.32. A galvanic cell generates on a potential of 0.32 volts when operated under standard conditions. According to the reaction above, which of the following pairs of conditions are needed to construct a similar that generates lower cell potential? The lowest cell potential. So if we're trying to, this is very similar to the last one. If we're trying to drop E cell, we have to drop the LNK, right? Or in this case, the LNQ, because we're changing the number. We're causing stress. So we have to drop the LNQ. How do we drop the LNQ? You need more reactant and less product, okay? More reactant and less products. And let's look at your Le Chatelier seesaw. You get Fe2 plus, you get Zn2 minus. I need more reactant. How do I get more reactant? Well, if I add a bunch of Zn2 plus, I will create more reactant to get back to equilibrium. Therefore, I will drop the E cell. Okay, so who gives me the largest amount of Zn? Look, these are both the largest amount of Zn. Who gives me the smallest amount of Fe? That's here. The correct answer is C. Okay. Okay. All right.